Welcome to the video on electrophilic aromatic substitution. Electrophilic aromatic substitution, or EAS, happens when we have a benzene ring. Recall, with an alkene, you can have addition across that double bond where the double bond, in fact, disappears. And we add one thing to each of those carbons. For electrophilic aromatic substitution, we do not break that double bond and add across it. Instead, the reaction that we will be talking about in this chapter is substitution. Benzene is reactive, but in a substitution reaction. We can replace one of the hydrogens that is on that benzene in a substitution reaction. This is a very versatile reaction. We can do halogenation, nitration, sulfonation, alkylation, or acylation. And those are the reactions that we will learn in this chapter. The general mechanism that happens with electrophilic aromatic substitution is that the nucleophilic double bond reaches out and forms a new bond with the electrophile, kicking out what I will call the conjugate base. The intermediate has that electrophile attached and a carbocation. That carbocation intermediate is resonance stabilized, and this is called the sigma complex. In the last step of the reaction, the other half of the electrophile, or what I will call the conjugate base, is going to pull off the proton that is on the carbon where our electrophile added, and then those electrons are going to kick back in. And this step brings back the benzene. So we have that beautifully stabilized aromatic system of the benzene with our electrophile added now. This is the general scheme for electrophilic aromatic substitution. We will see this over and over and over again in this chapter. The only difference is that we will have to figure out which electrophile we need to use in order to make the specific reaction happen that we're talking about. Now, because benzene is so stable, we are going to need to have some pretty crazy good electrophiles for this reaction to get going. And so as we walk through the chapter, we will be determining what crazy good electrophile we need in order to make this reaction happen in order to get the desired product. So in general terms, we can talk about electrophilic aromatic substitution in this way. We have a double bond of our benzene acting as the nucleophile, reaching out and forming a new bond with that electrophile. Once that happens, we form the carbocation intermediate, which is resonance stabilized in this sigma complex. And the final step is a proton transfer. We have that base performing a deprotonation so that we can have the two electrons in that bond hop back in, and we can bring back our benzene, restoring aromaticity. For halogenation, for example, where we're going to add a bromine to the benzene ring, we need to create our crazy good electrophile. And that crazy good electrophile is FeBr3. It is a Lewis acid catalyst, and the FeBr3, when reacted with bromine, Br2, gives us this positive bromine right here, which ultimately is going to be our crazy good electrophile. In order to substitute a bromine onto a benzene ring, we will use FeBr3 in the presence of Br2. In the first step, our double bond does nucleophilic attack onto the bromine that is partial positive, and we add our electrophile. This creates the sigma complex, which is a resonance stabilized carbocation intermediate, which then ultimately goes on to react with the FeBr4, and that deprotonates. So we have a proton transfer. The electrons in that bond hop back in to bring back our benzene, which is the final product. We have bromine added to the benzene. Please note, our crazy good electrophile for this reaction is FeBr3 in conjunction with Br2. A second example of a compound that will create a crazy good electrophile is AlBr3. And this reacts the same as the FeBr3 that I just showed you. We can also add chlorine by adding AlCl3 in the presence of Cl2, and that's going to be the same mechanism as the Br2 addition. We cannot add F2 or I2 in this manner. Fluorine is too violent and iodine is generally too slow. So chlorine and bromine are the two halogens that we can add in this way. This is just showing the same mechanism for the chlorination with AlCl3. So we have the nucleophilic attack of the electrophile. We add the electrophile there, creating our carbocation, our resonance stabilized sigma complex. And in the last step, our sigma complex is deprotonated, regenerating our benzene and restoring aromaticity. The second reaction that I'd like to talk about is sulfonation, where we add SO3 to our benzene ring. The crazy good electrophile is going to be formed by using fuming H2SO4. Fuming H2SO4 contains SO3 gas, shown here, and that is going to serve as our crazy good electrophile. So you may be getting bored with my description, but benzene does nucleophilic attack onto our crazy good electrophile, and it attacks that sulfur, kicking some electrons onto one of the oxygens. So we've now added the SO3 group to our benzene, and we now have this carbocation that is resonance stabilized in the sigma complex. The final step is proton transfer, and so we're going to pull the proton off that is on that carbon that has our electrophile, regenerating the aromaticity and bringing our benzene back. There is one extra proton transfer step that needs to happen in this reaction. We have a hydronium ion that is going to be used to protonate our O- and our SO3, giving us the final product shown here. Sulfonation is actually very sensitive to reagent concentration, and it is a reversible reaction. So we'll see later that we can use this in synthesis if we want to block one of the sites on the benzene ring. We can put the sulfate group on and then take it off. And the way that this is reversible, we have benzene. If we use concentrated fuming sulfuric acid, we end up with our sulfonation product. And if we use dilute H2SO4, that actually brings us back to the benzene. So sulfonation is very often not our final product, but as a means to get what we want. Next, we have nitration. Nitration occurs using HNO3 as our crazy good electrophile. And the way that we are going to do that is we are going to react benzene with nitric and sulfuric acid. When we have nitric and sulfuric acid reacting together, sulfuric acid is the stronger acid, so nitric acid is going to be protonated. We end up with this intermediate that then loses water, forming our nitronium ion. And this, my friends, is the crazy good electrophile. We have nucleophilic attack to that crazy good electrophile, nitrogen and the nitronium ion, giving us our sigma complex, which then gets deprotonated and bringing back our benzene. And in this case, we have nitrobenzene as our product. Because we have no direct way to make aniline, what we can do is reduce the nitro group. So if our desired product is aniline, we can take that nitrobenzene and react it with either iron or zinc in HCl, followed by treatment with NaOH, and that reduces our nitro group to an amine group, and we have our aniline. So for the purposes of synthesis, if we started with benzene and we wanted to go to aniline, we would need to nitrate first, and then we would have to reduce our nitro group to the amine in this way. Next, we will talk about alkylation. So this is when we're adding just a carbon group. And the way that we're going to do this is we're going to use an alkyl halide as our crazy good electrophile. We're going to create that crazy good electrophile by using AlCl3 as a Lewis acid catalyst. So the general scheme for this reaction is going to be we react benzene with your alkyl halide in the presence of AlCl3, and we attach the alkyl group to the benzene. The way that AlCl3 creates that crazy good electrophile is shown here. The alkyl halide reacts with the AlCl3 to give this intermediate, and it turns out this is a way to have the halogen leave, giving us a carbocation, and that carbocation is the crazy good electrophile. So once we have that crazy good electrophile, we are going to have nucleophilic attack, creating our sigma complex, ultimately have a proton transfer, bringing back our benzene and giving us our alkyl benzene product. This reaction works successfully with primary halides. But wait a minute, primary halides don't work because it's hard to make a carbocation from that. And the way that this happens is that the electrophile, our carbocation, is presumed to be part of a complex. So I hope you're thinking, but wait, if we have a carbocation, isn't that susceptible to rearrangement? And the answer is yes. So if you want to add a 4-carbon chain to a benzene ring and you want to add it at the end of the chain, we will not be able to have that happen. You are going to have a rearrangement. If you had this 1-chlorobutane and you create your carbocation, we are going to have a hydride shift and the carbocation is going to become secondary. So even though this may be your desired product, the majority of the product is going to have had the rearrangement happen. So Friedel-Crafts alkylations undergo carbocation rearrangements, and so we're going to get a mixture of products. There are other limitations with Friedel-Crafts alkylation, and that is the fact that we are limited in the alkyl groups that we can add. For example, we cannot form a carbocation on a double bond and or on a benzene ring. So we are not able to add double bonds and or benzene rings. In order to form the carbocation, we need an sp3 hybridized carbon. Another limitation is that once we add one group on, it actually makes that more reactive, so a second group is going to add. So we are going to have polyalkylation happen as well. And the third limitation is that this reaction is actually very sensitive. And so we will learn later in the chapter that some aromatic rings are deactivated. In other words, they have groups on them already that make it so that the double bonds on the benzene ring are less nucleophilic. And nitro is very well known for deactivating benzene rings. So if we have a nitrobenzene, we cannot have alkylation because that reaction is too sensitive, and this nitro group makes this benzene ring too deactivated to react. And next, I want to talk about Friedel-Crafts acylation. And Friedel-Crafts acylation is, instead of adding an alkyl group, we are adding an acyl group, which is a C double bond O with an R. And so this reaction happens very similar to the alkylation. We are going to add our acyl chloride with AlCl3. And so the mechanism here is very similar to the alkylation. We have that chlorine reacting with the aluminum and AlCl3. And in this case, we end up with the positive charge on the carbon here, which then gives us this reactant that is going to react with benzene. Please note that this acylium ion is resonance stabilized, but that positive charge can be delocalized. So we have benzene ring doing nucleophilic attack on our crazy good electrophile. We have the sigma complex resonance stabilized carbocation, and then we finally have a proton transfer, which restores our aromaticity and brings back our benzene. Now, Friedel-Crafts acylation can actually help us overcome the limitations of Friedel-Crafts alkylation, because once we have this carbonyl group added to our benzene, we can use zinc and or mercury in HCl and heat to reduce that carbonyl down to the alkane. So this would be a way that we can add a 4-carbon chain at the end. Instead of doing alkylation, which would have rearrangements, we do acylation and then reduction. And this specific reduction is called Clemmensen reduction. So the problem that we had in alkylation, where we had multiple groups adding, does not happen with acylation. So polyacylation is not typically observed. So there you have it, electrophilic aromatic substitution. We can make a whole bunch of different things from benzene. The mechanism seems a little repetitive, except for we have to learn how to make that crazy good electrophile for each reaction.